Hello everyone, welcome to Math 115, College Algebra. So in this section, 5.1, we're going to talk in particular about quadratic functions. And the graph of a quadratic function is a parabola, so we'll also describe some characteristics of parabolas and different ways that we can represent a quadratic function, something called the general form and then something called the vertex form. Okay, so let me start just by recognizing some characteristics of a parabola. So on this picture here, I have a graph of a parabola. So this is a graph of a quadratic function. And notice that there's a couple of important points on here. So first of all, a parabola is always going to have either a lowest point or a highest point, depending on whether it opens upward or downward. In this case, the parabola opens upward and it has a lowest point, and that lowest point is called the vertex. Okay, so in this case, and I have it labeled here, this point right here, this is the vertex. And it has the coordinates 2, -3. In general, the vertex is going to have the coordinates h, k. Okay, so in this case, h is 2 and k is -3, right? It's the lowest point of that parabola. If the parabola were to be upside down like this, let's say it looked like this instead, then this point right here would be the vertex, and it would be the highest point of the parabola. Right? Again, it would have coordinates h, k. All right, what else? There's definitely a y-intercept. So there's always going to be one y-intercept. So that's this point right here. In this case, the y-intercept happens to be 0, -5/3. And then a parabola may or may not have x-intercepts. In this case, there's two x-intercepts. So there's one right here, right at the point -1, 0, and there's one here at the point 5, 0. But depending on the parabola, let's say we have a parabola that looks like this. In this case, since the graph never crosses the x-axis, there are no x-intercepts. Right? Or we could have a case like this, where the graph just touches the x-axis. Let's say it does that. In this case, there's only one x-intercept, and we'll talk about this later, but this is called like a double root or double zero. Okay, so there's just one x-intercept in that case. But we could also have the case, as in the main picture here, where we have two x-intercepts. So you could either have 0, 1, or 2 x-intercepts. And then there's also something called the axis of symmetry, right? So if you look at this green dashed line here, about this axis, this parabola is symmetrical, right? If you flip it about the axis, it'll look exactly the same. It's like a mirror image about the axis. And the equation, since it's a vertical line, is going to be x equals a constant. And the equation is always x equals h, right? So remember, in this case, h was 2, right? We found that from the vertex there, so h is 2. So the equation for the axis of symmetry is going to be x equals 2, which I have in green over here, but I'll write it again. So x equals 2. That would be the equation of the axis of symmetry. All right, so those are sort of the important characteristics of a parabola. It has a vertex, which is either the highest or lowest point, and the coordinates are h, k. It always has a y-intercept, and it may or may not have x-intercepts. It could have 0, it could have 1, or it could have 2. And then the axis of symmetry has the equation x equals a constant, and it's x equals the h, right? Because it's going to be a vertical line. Okay, so given that, let's see if we can answer the questions in this first example here. So I want to determine the vertex, the axis of symmetry, any zeros, right, or x-intercepts if there are any, and then the y-intercept of the parabola shown here. So definitely the vertex, right? In this case, it opens up again, so the vertex is the lowest point. That's the point right here. So it has coordinates 3, 1. The y-intercept is where the parabola crosses the y-axis, so that's this point right here. Right, so this is the y-intercept, and it has coordinates 0, 7. In this case, again, because the parabola does not cross the x-axis, there's no x-intercepts. Right, or you could say no zeros is another way of saying it. And the axis of symmetry is going to be about this vertical line right here. I'll dash it in green. And it has, again, the equation x equals h. And remember, h is the x coordinate of the vertex, so x equals 3 is the equation of the axis of symmetry. So x equals h or x equals 3. And because it opens upward, the vertex is a minimum in this case. And basically, when we see the equation, the quadratic equation, the a will tell us the direction of how it opens. If the a is greater than 0, it opens upward. So in this case, we're going to see later that this parabola must have had a quadratic equation where the a was positive, right, greater than 0. Okay, when we write the quadratic function in equation form, there's 2 different forms that we typically use. So one's called the general form, and it's given as f of x equals ax squared plus bx plus c, right? How do you know that this is a quadratic function? It's the squared term, right, that makes it quadratic. If we didn't have that, then this would just be a linear equation. If we didn't have the first 2 terms, it would just be a constant equation, right? So it's really the exponent that determines what type of function it is. So that's definitely a quadratic equation. Then it turns out, and I won't show this, but it turns out if you use completing the square, you can rewrite this in this form right here. So the a is the same. Then I have the quantity x minus h squared plus k. And in this case, the h comma k, that is going to be the vertex. So that ordered pair represents the point of the vertex. Okay, again, the a determines whether the parabola opens upward or downward. If the a is positive, it opens upward. If the a is negative, it opens downward. And again, by completing the square, you can show how to find the h and the k values. The h is equal to, so if I go back to the general form here, the h is given by minus b over 2a. So if I use the coefficients from the general form, I can find the value of h, which is the x coordinate of the vertex. And then to find the k, the easiest way to find the k is once I find h, I can substitute it in to the function, and the output must be the k, right? Because it's h comma k. The input is h, the output is k. So if I calculate f of h, and remember h is negative b over 2a, that will give me k. All right, that's the easiest way to find k. It turns out that you can also find k in terms of a, b, and c. And it's given as c minus b squared over 4a, but hardly anyone ever uses this. They literally, once they find h, they plug it into the function, and that gives you k. That's a much easier way to find k, okay, which is like the y coordinate of the vertex. All right, so let's do some examples of this. Let's say I'm given a quadratic function, and it's in general form. Okay, so x squared minus 12x plus 32. And I want to put it into vertex form, right? So I want to convert that into vertex form. So first of all, what are a, b, and c in this case? Well, a is 1, right? A is the coefficient of the x squared term, so a is 1. B is negative 12. And c is positive 32. So let me first find h. Well, remember, to find h, it's always going to be minus b over 2a. So I have minus a negative 12 over 2 times 1. Well, that's going to be positive 12 over 2, which is equal to 6. So h is 6. All right, so that's the x coordinate of my vertex. How do I find the y coordinate? How do I find the k? Well, the k is always going to be the function evaluated at h, right? If the input's h, the output must be k. So to solve this, I'm going to find f of 6. So I go to my function, and I can do this in the general form. And where I have an x, I'm going to plug in a 6. So I have 6 squared minus 12 times 6 plus 32. If you work this out, this is 36 minus, what's that, 72 plus 32. So this is going to be negative 36 plus 32. So it looks like my k is equal to a negative 4. Okay. Now, I want this ultimately to be in vertex form. But now I know my a, right? The a is the same as before, right? So the a is still 1. I know my h, and I know my k. So if I write this in general in vertex form, it's a times x minus h squared plus k. So y equals 1 times x minus 6 squared, and then plus a negative 4, you can write as negative 4, right? Minus 4. So that's my answer. So we don't really need to write the 1, right? So I can write this as y equals x minus 6 squared. Hold on a second. Make that a little cleaner. Squared minus 4. So that would be same equation, the same quadratic equation, but in vertex form. X minus 6 squared minus 4. Okay. How could we, let's say we're given a quadratic equation in a general form, and we want to try and sketch the graph of it, or I want to try and draw the parabola. Well, it's much easier if we know the vertex and maybe finding the y-intercepts or the x-intercept that'll help us sketch it. So it'll be easier if we can just put it in vertex form, right? Or we can just find the vertex by using h as negative b over 2a and then evaluating the function at h. If we have the vertex, we have the x-intercept, we have the y-intercept, then we can easily graph that parabola. All right, so let's try an example here. So here's my quadratic function in general form, right? X squared plus 4x plus 3. And I want to graph this function. So first of all, I know that a is 1, right? B is 4, and C is 3, right? Because it's in general form. So in order to graph it, let's find the vertex, let's find the x-intercept, let's find our x-intercepts possibly, the y-intercept, and then the axis of symmetry. So for the vertex, at first I'm going to find h. So h is negative b over 2a. So it's negative 4 over 2 times 1. Well, that's going to be negative 4 over positive 2, which is negative 2. And then to find the k, that's equal to f evaluated at h, right? So that's f of negative 2. So in this case, that'll be negative 2 squared plus 4 times negative 2 plus 3. So that'll be positive 4, right? Minus 8 plus 3 That's negative 4 plus 3, which is negative 1. So I know that my vertex is going to have the coordinates negative 2, comma, negative 1. Right? So that's good. So we know 1 point definitely on this parabola. We also know from this that the axis of symmetry is going to be x equals h, right? So it'll be the line x equals negative 2. Okay, what else? So let me just highlight the important things. That's going to be important. I don't really need to know that, but I'll just put that there. So axis of symmetry is x equals negative 2. Let's find the y-intercept. The y-intercept is pretty easy to find, right? To find the y-intercept, I set my x equal to 0 and I solve for y. Right? So basically, the y-intercept is going to be, what is the value of the function when x is 0? So I want to evaluate it at 0. Well, that's 0 squared plus 4 times 0 plus 3. So it's just going to be 3, right? This is equal to 3. So I know that the point 0, comma 3 is my y-intercept. Okay? And then does this have any x-intercepts? So let's go back and see if we can calculate the x-intercepts. Well, how do I find the x-intercept? Let me do this in black. I set y equal to 0, but remember y is the same as f of x, right, equal to 0, and then solve for x. So just like we've been doing for many, many, many different examples, right? So I'm going to set the entire function x squared plus 4x plus 3 equal to 0. Solve it for x. Well, it's a quadratic equation, so I'm going to try factoring. So I have x and x. I want two things to multiply, give me 3, and add, give me 4. That's easy, right? Positive 3, positive 1. So one possibility is x plus 3 is equal to 0, and the other possibility is x plus 1 is equal to 0. This one is going to give me the solution x equals negative 3. And this one will give me the solution x equals negative 1. So one x-intercept is negative 3, comma 0, and the other one is negative 1, comma 0. Okay, so in this case, the parabola does pass through the x-axis in two different places. Put a comma there, right? There are two separate x-intercepts. Okay, what else do we know? Well, we know since a is positive, right? 1 is greater than 0. It opens upward. So it opens upward as well. All right, so given all the information, let's see if we can graph this. So I'll draw a coordinate system here. Put some tick marks. I don't really know how many I'm going to need. So this is x, this is going to be y, or you could say f of x. Now, what are the points? Well, the vertex was at, where was it? Negative 2, negative 1, right? So I go to left 2, down 1, so that's like right here. And then the y-intercept was 0, 3, so that's right here. The x-intercepts were negative 3, 0, and negative 1, 0. So here and here. So it looks like, just from that, we can definitely draw a parabola, right? It's going to look something like this. It'll go up. And then this, it's hard to draw this, but this will curve around and go up like that. And then also we knew, we don't have to draw this, but the axis of symmetry is x equals negative 2, right? So it's that vertical line, that green dashed line is a vertical line. So that's what the parabola looks like, right? That's the graph of that quadratic function. Okay, we drew the vertex, we drew, in this case, the x-intercepts or the zeros, and we drew the y-intercept. I wasn't very clear on this, but that goes to that 0.03. Okay, let's do another one of those. Okay, so in this case, I want to sketch the graph of this quadratic function. So it's already in vertex form. So basically, we can just read off a bunch of information here. First thing, I know that A, remember the A is the coefficient in front, which is a -1/2. So since A is equal to -1/2, and that's less than 0, this is going to open down. So definitely the parabola is going to open downward. What else do I know? Well, if I look at the H, remember, if this has the form, let me write the general form here. So g of x is equal to a times x minus h squared plus k. So you got to be a little careful with this, right? Because it's x plus 3, if I want to write this as x minus h, then the h must have been a -3, right? You can think of this as, this is equal to -1/2 x minus, because I want it in that same form, minus a -3, right? That's the same as x plus 3 squared plus 2. So this is telling us that h is equal to -3. And it's also telling us that the k is equal to +2. So I know the vertex has the coordinates -3, 2, right? H, k. What about the y-intercept? So to find the y-intercept, I'm going to set x equal to 0 and solve. So I want to basically find g of 0, right? So this is going to be -1/2 0 plus 3 squared plus 2. So let's see, 3 squared is 9, right? So this is like -9/2 plus 2. So that's -9/2 plus 4/2, which is -5/2. Right, I can write 2 as plus 4/2. So this is -5/2. If you want to write it as decimal, it's -2.5. Let me write that cleaner here. So -2.5. Okay. All right, that's good. So we know the y-intercept. We know the vertex. We could probably draw it right now, but let's see if we can find any x-intercepts. Does it have any x-intercepts? So to find the x-intercept, I'm now going to set the entire function equal to 0, right? G of x is equal to 0. So that means I have -1/2 x plus 3 squared plus 2 is equal to 0. All right, I guess the easiest way, I could expand this out, but you don't need to do that. Let's use the square root property. So first I have to isolate the square part. So I'm going to subtract 2 from both sides. So I have -1/2 times x plus 3 squared is equal to -2. Then I'm going to multiply both sides by -2, or that's the same thing as dividing by -1/2. Right, so I have x plus 3 squared equals, and then -2 divided by -1/2 is +4. And now we can use the square root property. I'm running out of room here, but so square root of x plus 3 squared equals, remember it has to be plus or minus the square root of 4. So I'll go up here to finish it. So now I have x plus 3, right? So square root of x plus 3 squared is just x plus 3. And that's got to equal plus or minus square root of 4 is actually just 2. Then I'll subtract 3. So it looks like one possibility is x equals 2 minus 3, which is -1. And the other possibility is x equals -2 minus 3, which is -5. So my two x-intercepts are going to be -1, 0 and -5, 0. to the 0 here. Okay, so if I put all this together, I'm going to squeeze the graph in this little corner here at the side here. Okay, so let me draw some tick marks. 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so I know my vertex is at -3, 2, right? So if I go to the left 3, up 2, that's going to be like right here. -3, 2. Then my y-intercept was 0, -2.5. So that's kind of like right here. And then I had an x-intercept at -1, 0, which is right here. Again, it's really hard to draw this really well by hand, freehand. But if you use like Desmos or something, it'll do perfect for you. And then what's the other x-intercept? -5, 0, right? So that's right here. So this parabola is going to look something like this. Going to go on forever. This goes through this point right here, right? And then this side goes on forever. So something like that, right? It opens downward. We knew that because the A was negative. It was -1/2. Okay, great. So what is the domain and range of a quadratic function? Let's talk about that next. So remember, for any polynomial, there's no issues, and a quadratic function is just a polynomial function of degree 2. There's no issues with the x values, right? You can plug in any x. You're not dividing by 0. You're not taking the square root. So any x will work. So it turns out the domain of a quadratic function is all real numbers. And remember, I can write that as parentheses, -infinity, infinity, right? So all real numbers is always going to be my domain of a quadratic function. Now, what is the range? Well, the range depends on whether it opens up or down. If it opens upward like this, then it has a minimum value. And remember that k, that's like the minimum y value. So in this case, the range, it would go from k all the way to positive infinity. If it opens down like this, then the range goes from negative, because we always start with the small number. It goes from -infinity all the way up to k. All right, so in this case, my range is going to be from bracket 1, right, because that's the k value here. Remember, it's h, k, so that's the k is 1, to infinity. In this case, so for this parabola, which opens downward, my range is going to go from -infinity, because I always start with the low, and it goes up to k, which in this case is 4, right, including k. Okay, so in general, if the parabola opens upward, let's draw a picture like that, right? Then, in other words, a is greater than 0. Then the range is going to be from k to infinity. If it opens down like this, so a is negative, right, less than 0, then the range is going to start from -infinity and go up to k. Always including the k there, right? So it's going to bracket around the k. Right? And just remember, k is the y value of the vertex. Okay, so not too bad, right? Let's do a couple of examples with this. All right, so we're given a quadratic function, in this case negative 5x squared plus 9x minus 1, and we want to find the domain and range and then state any absolute extrema. Okay, so the domain, again, the domain for any quadratic function is going to be all real numbers, right? So the domain is all real numbers. And how do we write that? We write it negative infinity, comma, infinity. Right, that's the domain. For the range, well, I need to figure out what k is, right? So let me first find h. So this is in general form, right? I want to find h, but that's always going to be minus b over 2a. In this case, a is negative 5, which actually tells us it opens downward, right? B is 9, and C is negative 1. So I have negative, I guess, 9 over 2 times negative 5. That's kind of messy. Okay, so it'll be 9/10, I guess, right? Positive 9/10. And then if I want to find k, that's going to be the function evaluated at h, right? Evaluated at 9/10. So this would be negative 5 times 9/10 squared plus 9 times 9/10 minus 1. Okay, so let's work this out. A little bit of a pain just to deal with these fractions. So this is what, 81 over 100 plus, I guess, 81 over 10 minus 1. And if I want to write everything in terms of over 100, so it has the lowest common denominator, I can write this as, so negative 5 times 81 is negative 405 over 100. Then if I multiply the second term by 10, I have plus 810 over 100. And then 1 I can write as 100 over 100. Right? And if you work that out, you're going to get 305 over 100, which actually simplifies. I guess 5 goes into both of them, definitely. Simplifies to 61 over 20. Okay, so that's k. All right, we know that this opens downward, right? And what tells us that? The a equals negative 5, right? So it opens down. So this thing is going to have, if I just draw a little sketch of it, it's going to have a vertex at the point 9/10 and then 61/20, which is like a little over 3. So somewhere, let's say it's like right here. Doesn't have to be exact. We just know that this thing opens downward like this. Okay, something like that. Actually, let me draw that a little better. Okay, so it has this point here, which has the coordinates h comma k, right? That's the vertex. So it's 9/10 comma 61/20, which is a little more than 3. And then from there it opens downward. Something like that. Okay, so that means that the range, remember the domain is all real numbers. Now the range is going to be from negative infinity, right? Because it opens downward, so that's the smallest value is like negative infinity. It's not even a value, right? It's just saying it goes forever downward. Up to k, but k was 61/20, right? Including k. So that would be the range. And when we wanted to find, are there any absolute extrema? Are there any absolute maximums or absolute minimums? Well, there's definitely no absolute minimum, right? Because it goes down forever. So no absolute min. But there is an absolute maximum. The absolute maximum is the vertex, right? So you could say there's an absolute max of, it has a value of 61/20 at x equals 9/10, right? It's at the vertex. And by the way, that's also a relative maximum too, right? Because that's where a hill is. So it's also a relative maximum. But since it's the highest point of the entire function, it's also an absolute maximum. So right at the vertex, we have the absolute maximum. Okay, another example. This one, again, is a little bit easier in some ways because it's already in vertex form. So find the domain and range of that quadratic function. It's already in vertex form. State any absolute extrema. Okay, so again, we know that a is equal to 2, right? So it opens up. I'm just matching, like this has the form f of x equals a times x minus h squared plus k, right? So h, it's already in the form x minus something, right? So h is the 4/7. And then k is the 8/11. Okay, so the vertex has coordinates h, comma k. All right, so that's nice. So we know it's going to look something like this, right? If that's the vertex, so 4/7, comma 8/11, somewhere in here, let's say. So that has coordinates 4/7, 8/11, right? It's the vertex. And this is somehow going to open upward like this. We could find the y-intercept. Looks like there's no x-intercepts, right, in this case. We could find the y-intercept, but we don't need it to state what the domain and range are. So first of all, what's the domain? Well, the domain is all real numbers, right? So the domain is going to be from -infinity to infinity. There's no restrictions on the inputs, right, on the x. And then what is the range? Well, it opens upward. So it starts at k, including k, so it's going to be 8/11, right, with a square bracket, and it goes all the way to infinity. And then what are there any absolute extrema? Well, in this case, since it goes up to positive infinity, there's no absolute maximum. But there is an absolute minimum of 8/11 at x equals 4/7. Right? Again, it's going to be at the vertex. Okay, so there's an absolute minimum of 8/11 at x equals 4/7. And it's also a relative minimum as well, right? Because that's where a valley is. Okay, so hopefully you've gotten the hang of looking at some of the characteristics of a parabola which represents a quadratic function. All right, the last thing I want to look at, and we're only going to do a couple of examples of this, is some applications that involve quadratic functions. Usually these applications involve finding a maximum or a minimum, like optimizing. And we know with a quadratic function, which is represented by a parabola, the maximum or minimum is going to always be the vertex, right? If it opens upward, then this would be a minimum. If it opens downward, then the vertex would be a maximum. Okay, so that we're kind of, these applications are going to involve writing a quadratic function and then basically finding the vertex, finding the maximum or minimum. Okay, so let's do an example. Okay, so this example says Maria wants to enclose a rectangular space in her backyard for a new garden. She's purchasing 80 feet of wire to enclose 3 sides, and she'll use a section of the fence on the edge of her property for the 4th side. What dimensions should she make her garden to maximize the enclosed area? Okay, so this is the idea. I'm going to draw a picture here. So this is like the fence that already exists. Let's draw it like this across. So this is the fence on edge of property. Okay, that's like the 4th side of her garden. And then what she wants to do is have a rectangular garden where she has to put up the other 3 sides, right? So these are the other 3 sides. Okay, well, we want to maximize the area, right? And first of all, we need to give variables for these sides. So typically with a rectangle, you label them length and width. So I'm going to call this the length, and then these 2 sides are the width, right, of that rectangle. All right, we want to maximize the area. So that means we need an equation for the area, right? So the area is going to become our quadratic function ultimately. So then we're going to want to find the vertex, right, to find the maximum. So what is the equation for area of a rectangle? Well, we know in general that area is equal to length times width, right? So it's L times W. However, we want to write this area equation just in terms of one variable, either L or W. It doesn't matter which one, but just in terms of one variable, right? We don't want it related to 2 variables, just one variable. So how do we do that? So first of all, let me write that here. So we need to write area in terms of one variable. Why do we do that? Because we're considering area to be a function of just one variable, either the width or the length, right? And then we can graph it as a parabola, and we can find the vertex. Okay, so how do we do that? Well, there's more information given here, right? We're also told that Maria purchases 80 feet of wire to enclose the 3 sides. So we know now that the total amount of wire, which is going to be the total amount of fence, is equal to W plus L plus W, and we know that's equal to 80 feet, right? So if you think about it, right, I need this width, so I need that much wire, then I need this length, and I need this width. So W plus L plus W, that's got to equal 80 feet. And then I can simplify this. I can write it as 2W plus L is equal to 80. Okay, so now I want to solve for one of these variables, and L is probably the easiest to solve for because it's already kind of isolated, right? It has a coefficient of 1 in front. So I'm going to subtract 2W from both sides and solve this for L. So I'm going to get L is equal to, I'll write it as minus 2W plus 80. All right, why did I do that? So notice now, if I substitute that L in for the L in my area equation, so this L is going to go into here. It's going to substitute in. Now I can rewrite my area equation just in terms of W. So now this becomes A equals L is negative 2W plus 80 times W, right? I still have to multiply by this W here, so times W. I can distribute in that W, so I'm going to have A is equal to negative 2W squared plus 80W. And so now my function is just in terms of W, which is what I want, right? I basically have a quadratic function where A is a function of W, of the width. Okay? You could actually even plot this. Let's find out some more about this before we plot it, but I will plot this to show you that how this all makes sense. Okay, so now area is just in terms of W, and it's a quadratic function. So now the area is in terms of W, and it's a quadratic function. Notice, right, we know A and B, right? A is negative 2 and B is 80. So because the A is negative 2, we know it opens downward. Right? A is negative 2, B is 80, and actually there is no constant, so C is 0. But the A equals negative 2 means it opens downward, which means it has a maximum, right? The vertex is going to be the maximum. So our goal here is to find the vertex. Okay, well, I can do that, right? I can find, first I'll find the H, which is really like the W component of the vertex. So this is going to be minus B over 2A, right? So it's minus 80 over 2 times negative 2. So that's going to be negative 80 over negative 4, which is positive 20. And then to find the K, that's going to be the function A evaluated when the width is 20, right? Evaluated at H, basically. So this will be minus 2 times 20 squared plus 80 times 20. So if you work this out, this is negative 2 times 20 squared is what, 400? And then plus 80 times 20 is 1600, right? 1600. So I have negative 800 plus 1600. That's equal to 800. So K is equal to 800. So this tells us that the vertex is going to be 20, 800. Right, so it's 20, that was the H, comma K. Right, it's always H, comma K. All right, so actually this answers our question, right? The H is the width that we want to maximize the area, right? Because I found the vertex. So I'll write it here. So for the maximum area, or I'll say area is maximum when the width is equal to H, right? So it's when the width is equal to 20 feet. And then how do we find the corresponding length? Well, I have this equation up here I can plug back in, right? I know the length is negative 2W plus 80. So this is negative 2 times 20 plus 80. So it's negative 40 plus 80, which is positive 40. So the area will be maximum when the length is 40. Okay, so that's the answer to the question here. If we make this width 20 feet and we make the length 40 feet, and this is also the width, so 20 feet, then we'll get the maximum. This area here will be the maximum that it can be. It's kind of interesting, right? So the length is like twice the width in this case. Notice everything makes sense too, right? The amount of fence is 20 plus 40 plus 20 is 80 feet, right? That makes sense. And you're going to end up with a maximum area. So any other widths and lengths that satisfy the width plus length plus width equals 80, any other widths and lengths that aren't 20 and 40 will not maximize the area. Okay, this will maximize the area. Because there's many other, right, widths and lengths that you could have for the fencing to make a rectangle, but we wanted the ones that would maximize the area. And then I said I would plot it. So let's actually plot this function, the area function. See if I have a little more room here. So if I plot this, it's going to look something like this. So this is the width, right, on the x-axis, and then area is on the y. And one of the points that it passes through is when the width is 0. So if I plug in 0 here, here's my equation. If I plug in 0 for width, I'm going to get 0 for the area. So that's 1 point is 0, 0. And then it also turns out when the width is 40, if I plug in 40 here, so 40 squared times negative 2 plus 80 times 40, that's also equal to 0. So this point right here at 40 is also going to be 0. And then we know what the vertex is going to be 20, comma, this is not to scale, comma, let's see, what is my vertex? Is it 800? Yeah, 800, right? Oh, I made a mistake over here. This is not 20, 80, this is 20, 800, right? The K was 800. So this is going to be 800, and the parabola will look something like this, right? So that's the vertex, 20, 800. Parabola is going to look something like this. And come back down. Okay, so actually this is interesting, right? So notice here that if the width were 0, then the area would be 0. If the width is something between 0 and 20, there's definitely some area of that rectangle, but it's not the maximum. It's only when the width is 20 do you get a maximum area. And the maximum happens to be 800 square feet. Okay, let's do one more problem of this type where we have to maximize or minimize a quadratic function, which essentially again means finding the vertex. Okay, so this is sort of a problem from physics that comes up a lot. So physics or biomechanics, anywhere where you have like the motion of an object. In this case, it's the motion of the object in a gravitational field, right? Under the influence of the Earth's gravity. Okay, so you're told in this case that a ball is thrown upward from the top of a 40-foot building at a speed of 80 feet per second. The ball's height, y above the ground, can be modeled by the equation y of t equals negative 16t squared plus 80t plus 40. T, by the way, is the time in seconds. So basically this is giving us the vertical position of the ball for each time in seconds. And we want to answer several questions about this. We want to figure out, when does the ball reach its maximum height? What is the maximum height of the ball? And then when does the ball hit the ground? Okay, so first of all, this is a quadratic function, right? And by looking at that, it's in general form. So by looking at that equation, we can see that A is equal to negative 16, B is equal to 80, and C is equal to 40. And the negative 16 tells us that it opens downward, which is good, right? Because that means that there's going to be a maximum here, right? There's going to be a maximum height, right? So Y, because it opens downward, Y here is going to have some maximum. And where is that maximum going to occur? It's going to occur at the vertex. Okay, so the first thing we want to do is we want to find the vertex. All right, so to do that, let me calculate h. So that's negative b over 2a. So in this case, it'll be negative 80 over 2 times negative 16. So it's negative 80 over negative 32. And if you work that out, it'll be positive, and I guess it's 2.5. I'll just write it as a decimal. So positive 2.5. And remember, the x variable, right, which we're finding the vertex, the h is the x component, but in this case, our x variable is named t, right? It's the time. So really, this is 2.5 seconds. It's going to be the time when the ball reaches the highest point. And then to find k for the vertex, I just plug in h. So this will be y evaluated at 2.5 seconds. So I have negative 16 times 2.5 squared plus 80 times 2.5 plus 40. If you work that out, that's going to be 140 feet. Okay, so basically we've kind of answered the first two questions, right? The ball reaches the maximum height. So the ball reaches the maximum height at a time of 2.5 seconds, right? It's when the time equals h, because that's the t component in this case of the vertex. And then the maximum height is the k, right? So the time again was the h of the vertex, and then the ball has a maximum height. So the ball's maximum height is 140 feet, which is really just our k, right? So the vertex told us a lot of information. It told us when the ball reached the maximum height and then the actual maximum height. Okay? Again, if you wanted to plot this, it would look something like this. So in this case, there is a y-intercept, right? How do I find that? Well, if t is 0, I plug in 0 here, 0 here. I'm going to get y is equal to 40, right? So there's definitely a y-intercept at this point right here of 0, 40, where, remember, the x-axis is my time, right, in seconds. And then the y-axis is what we're calling y, the vertical position in feet. The vertex is going to occur at 2.5, so it's like here, right? 2.5 comma 140. So wait, I'm not really drawing this to scale, but like way up here, let's say it's 140. So this would be the vertex. And then the parabola is going to look something like this, right? It'll go up, come back down. Something like that. Okay. So by finding the vertex here, which again was 2.5 comma 140, we've answered the first two parts of the question. Right? When does the ball reach the maximum height? When the time is 2.5. What is the maximum height? That's the K. It's 140 feet. Okay, what about the last question? When does the ball hit the ground? So that's got to be where the position, the Y, is 0, right? And we don't want to go, if you look at this, there's actually two places where the position is 0, right here and somewhere in here. But we don't want to go backwards in time. We're going to find that we're going to get a value here for, it's going to be like a negative time value. But that one doesn't make physical sense. We just want to go forward in time. So we really want this point right here. So what is the time when Y equals 0? That's when the ball hits the ground. All right, so basically we need to solve for that. So let's think about that. So make some room here. So for part C, when the ball hits the ground, Y is equal to 0. So what we can do is we can solve for t when y equals 0, right? We're going to set y equal to 0 and solve for t. So basically that equation is negative 16 t squared plus 80t plus 40 is equal to 0. All right, this is a quadratic equation, right? In terms of t, we can solve it. We can't easily, it doesn't look like we can easily factor this, so we'll probably have to use quadratic formula to solve it. So let's do that. Although I would recommend just using technology. If you get something like this on a homework question, I would just use a calculator or use the computer or ask AI to solve it for you. So, but we could solve it using quadratic formula, right? So remember that's going to be t is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So let's see. So I'm going to have t is equal to minus b, which is 80, right? Plus or minus the square root of 80 squared minus 4 times negative 16 times 40. All over 2 times negative 16. All right, so kind of a pain here, but if you work all this out, right, so if you plug this into your calculator, you should find this is t is equal to negative 80 plus or minus, that term with the radical is going to simplify to 94.66 all over, and then 2 times negative 16 is negative 32. Right, so one solution is going to be t equals negative 80 plus 94.66 over negative 32. And that turns out to be actually negative 0.458 seconds. And then the other solution is going to be t equals negative 80 minus 94.66 divided by negative 32. And that turns out to be positive 5.46 seconds. And that's the one we want, right? Remember, if we go back to the picture of the parabola here. So this solution was the negative 0.458 seconds. That's like backwards in time. It doesn't physically make any sense to choose that one. We want this one, right? It was thrown at 0 seconds, and when does it hit the ground? It hits the ground at some positive time, and it was the positive solution that we got, 5.46. That's the one we want. But you can see where both of them come from, right? I'm just solving the quadratic equation. Where does this parabola intersect the t-axis? Well, at this point right here, which is negative 0.458 comma 0, and then this is positive 5.46 comma 0. Right, so just from physical arguments, we can eliminate this one, but this is the one we want. Right, so that's when the ball hits the ground. So the ball hits when the time is approximately, because I rounded, 5.46 seconds. Right, that's when the ball would hit the ground. Okay, so yeah, it's a step up from doing applications with linear equations. Now we're using quadratic, so it's more complicated. And typically, again, these involve optimization, finding minimums and maximums, and that always involves finding the vertex, right, of that quadratic function. Okay, next time we'll talk, instead of focusing just on quadratic equations, we'll talk about polynomial functions and power functions, so more in general. Great, thanks.